In this video, I'm going to talk about transformers. Transformer is a static device which transfers electrical energy from one circuit to another circuit without changing frequency. It works on the principle of electromagnetic induction. So we learned that transformer is a static device. There are no rotating parts, so it's called static device, which transfer electrical energy from one circuit to another circuit without changing frequency. When it comes to the electrical engineering, there are three important missions. One is a generator. Generator is which converts mechanical energy into electrical. Mechanical into electrical. Another one is motor, electrical motor, which converts electrical energy into mechanical energy, whereas transformer, in simple way, XMER, it converts electrical energy into electrical. So it is not converting any other form. It is taking electrical energy and it is giving you back electrical energy. At the same time, it is taking AC voltage and it will give you AC voltage. It's not converting into DC or any other format. It takes AC voltage and it gives you AC voltage. And at the same time, if you have 60 Hz frequency, output is also 60 Hz frequency. Okay. Now, it is not converting energy into another form. Then why do we need a transformer? I will explain it to you in a simple example. Say, for example, we have a load center which is consuming 10 megawatts of power. Okay, here is the load center. It is taking 10 megawatts of power. Assume the voltage is 10 kV. Usually we don't see 10 kV voltage system. It might be around 11 kV or 13.3 kV. Okay, for calculation purpose, I'm just taking 10 kV. At the same time, most of the times you will see a three-phase system, but just for our convenience, I'm taking it as a single-phase system. Okay, so here is a single-phase system. Here is a power plant, a generator. Okay, this generator is supplying energy to the load. At the same time, assume that this generator is a little bit far away from the load center, maybe 10 miles. Okay, so this transmission system, assume that every wire will have some resistance. That resistance equal to R equal to rho L by A. Assume that is 1 ohm, including both wires. Okay, that 1 ohm resistance is for both wires. Now, what is the current passing through this? Assume that the power factor cos theta equal to 1. Assume the load we are turning on is resistive load. If it is resistive load, then our power factor is going to be unity. Now, P equal to V times I times cos theta. I already know P, which is 10 megawatt, and V is 10 kV. I, we don't know, cos theta equal to 1. So based on this, I equal to 10 times 10 to the power of 3 over 10 times 10 to the power of 6. Mega is 10 to the power of 6, 10 cube. You will end up with 1000 ampere. So this wire is carrying a 1000 ampere of current. Now, there will be, since the wire has some resistance, 1 ohm, and carrying some current, definitely there will be some power losses. So the power losses in the transmission line, power losses equal to I square times R. I square is 1000 square, R is 1. So the power losses are 10 to the power of 6 watt, which is 1 megawatt. Okay, so to supply 10 megawatts of power, we are almost wasting 10% of the power in the transmission system. At the same time, this generator has to supply how much? 11 megawatts of power. Okay, so out of 11 megawatts, 1 megawatt is wasted in the transmission line. Wasted in the sense that energy is going to be converted into heat energy. So this transmission line is constantly producing heat. What happens if it's constantly producing heat? The life of the transmission line is going to go down. At the same time, to supply 10 megawatts, you are generating 11 megawatts. That means you're providing extra mechanical energy or chemical energy. It could be coal power plant or hydropower plant or nuclear power plant. Whatever it is, you're providing extra energy to generate 11 megawatts. So we're kind of wasting a lot of energy in the system. Now what I'm going to do, I'm going to take the same system. Now I'm going to use a transformer. Okay, when it comes to the transformer, there are two types of transformers. One is a step up transformer, another one is step down transformer. So here I'm using two transformers. One is here I'm stepping up. So stepping up in the sense I'm giving 10 kV here and it will step up to 100 kV. I mean, I'm taking this transformer ratio. Now the second transformer, it will take 100 kV and step it down to 10 kV because my load is 10 kilovolt. Okay, so the voltage at this point is 100 kV. Okay, on the transmission line. Assume that this transformer 1 is very close to the generator, so this line is nothing, and same thing, transformer 2 is very close to the load, so this transmission line is probably the 10 kilometers, so 10 miles, what we discussed. So the resistance of this line is still 1 ohm. Now what is the current passing through the circuit or passing through the transmission line? I equal to P over V cos theta. I'm taking cos theta as 1, similar to the previous case. P is 10 megawatt, so 10 to the power of 6 over now 100 kilovolt. Okay, so now my current is only 100 ampere. Current passing through the circuit is only 100 ampere. So power losses in the transmission line are I square times R 100 square times 1, okay, which is 10 to the power of 4. I can say 10 kilowatt. Previously we were wasting how many kilowatt? 1 megawatt. 1 megawatt is nothing but 1000 kilowatt. Okay, so previously we were wasting 1000 kilowatts of power in the transmission line. Now it got reduced to only 10 kilowatt. Okay, it got reduced 100 times. Okay, so now you don't need to use that much mechanical energy on, I mean, we don't need to use that much mechanical energy on the generator side. At the same time, the power losses in the transmission line got reduced, so the life of the transmission line is going to go up. So this is the main advantage of transformer. It will reduce the transmission line losses. So according to working principle, we have two types of transformers. One is step up transformer, another one is step down transformer. So a step up transformer will have our V2, which is secondary voltage, is greater than V1. Step down transformer, which is V1, is greater than V2. Okay, where V1 is the primary voltage and V2 is the secondary voltage. So a simple transformer is going to look like this. There are mainly three parts. One is core. You can clearly see that's the core, made with iron, a good magnetic material. And secondary winding is connected to the load. Always, whatever the winding we connected to the load, we call it as secondary winding. Whatever we connected to the source, we call it as primary winding. So V1 or sometimes VP is the primary voltage. V2 or Vs is the secondary voltage of the second coil. I1 is the primary current or IP. Is or I2 is the secondary current. N1 number of turns on the primary and N2 are number of turns on the secondary. Okay, I'm going to talk about ideal transformer. When it comes to the ideal transformer, ideal means assuming there are no losses. Okay, even ideal transformer, based on the working principle, we have two types. One is step up, another one is step down. So ideal means power on the primary side, whatever we are giving on the primary side, will end up with on the same power on the secondary side. Okay, there are no losses. Now, when I was a kid, I used to assume, I'm from a small village from India. So in India, we used to get lots of power outages. Like we used to get only 10 hours of power in that small village, because the number of power plants are less there, power generation is limited there. So they wanted to supply energy to the more industrial area or more populated areas. So for villages, they used to cut down a little bit more time. So when I was a student, I used to think, okay, why can't we use transformers and generate more energy and supply it to the villages? Can we do that? We can't able to do that because, as mentioned, transformer will not generate any power. Second, that's the first thing. Second thing, you cannot create energy or destroy energy. Okay, so transformer cannot create energy, cannot destroy energy. So whatever we are giving on the primary side for ideal case, so this is winding 1. So whatever power I'm giving on the primary side, it will give you same power, or in reality little bit less power than the primary side. For ideal case, I'm going to take P1 equal to P2. Ideal case. So that indicates that V1 and I1 cos theta 1 equal to V2 I2 cos theta 2. Cos theta 1 cos theta 2 approximately 0, approximately same in ideal case. So V1 I1 equal to V2 I2. So whenever I'm stepping up the voltage, it automatically, oops,